So this is part 2 of topic 10, where we're going to start looking at word problems. So the first problem tells us that we have a fixed cost of $40,000 and a production cost of $8 for each unit produced. So we call this little c, and this is given a value of 8. This is part of the variable cost. Then we have the product sells for $12. So this is the selling price, and it is 12. We're told to find the cost function in part A. So for this, we're going to put together the variable part of the cost and the fixed part of the cost. The variable part of the cost is going to be coming from the cost per unit times the number of units. So for this, we're going to say it's the 8x. And then we're going to add to that the fixed cost of $40,000. This is our cost function. So for part B, we're asked to find the revenue function. And that is given for these linear functions simply by the selling price times the number of units produced, or X. That's our revenue function. Next, in part C, we're asked to put together the profit function. So the the revenue and minus the cost is how we get the profit. So that's just P equals R minus C. And we have each of these pieces. So we're going to go ahead and calculate that the profit function is the 12x minus the cost, and we're going to put parentheses around that so we don't want to lose any of the minus signs as we distribute them. So we're talking about minus 8x, the quantity 8x plus 40,000. Now we're going to distribute that negative sign through carefully. And we're going to get the 12 minus 8, if we group like terms, minus 40,000. And this is going to give us a profit function of 4x minus 40,000. Next, we're going to look at what is the profit or loss of corresponding production levels of 8,000 and 12,000 units. So the first thing we're going to do is we're going to go ahead and calculate the profit for 8,000. So we're just going to substitute 8,000 in, and we're going to calculate that and get 32,000 minus 40,000, which is equal to a negative 8,000. So the loss when we produce 8,000 is a loss of $8,000. And this doesn't say explicitly, but I'm going to assume it's for a month. So next we're going to calculate the profit associated with 12,000 units. And for this, we're just going to plug into our equation 4 times the 12,000, and then we're going to subtract the 40,000. And this was going to give us a 48,000 minus 40,000, which is going to equal 8,000. So we get that the profit for 12,000 units is $8,000. So first we were having a loss. Sorry, I misspelled that. We would have a loss of 8,000, and now we're going to have a profit of 8,000. So now we're going to go to problem 2. And this problem says, find the constants m and b in the linear function f of x equals mx plus b, such that f of 2 is equal to 4, and the straight line represented by f has slope equal to -1. So we're just going to write m equals -1. That's what that is saying. This is what it's telling us. So now we have 2 points and a slope. So we'll use our y equals mx plus b, substituting in 2 for x, minus 1 for m, and 4 for y. And we solve for b. So adding 2 to both sides, we see that b is equal to 6. So our function is -x plus, so the -1 is what's bringing in the negative in front of the x, and plus 6. For the next 2 problems, we're asked to find the point of intersection for each pair of straight lines. So for 3, we're going to see that the 2 lines are y equals 3x plus 4, and the second line is y equals -2x plus 19. When we look at the point of intersection for this, it's helpful to graph. So we're going to pull up some graph paper and go ahead and graph this out just to see if, when we do our math, it makes sense. So we're going to look at the line y equals 3x plus 4, and we're going to first graph that y-intercept at 4. And then we're going to use the slope of m equals 3. And actually I have to go up for a y-intercept of 19, which is pretty high. So I'm didn't give myself quite enough room here, but I'm hoping it's high enough. So counting by 2s, this is 10, and way up at the top is 18, so 19 is going to be in the middle between the 2 blue graph lines. Right here is our y-intercept for our second line. So going back to the first line, we'll put in a blue dot for that y-intercept. Now using the slope of 3, we're going to go up 3 and over 1, and then up another 3 and over another 1, and down 3 and to the left 1, to graph a few points that will enable us to draw this line. Next, we'll look at the line given by y equals -2x plus 19 that I have underlined in green, and we'll go ahead and graph that. Okay, so now we're going to focus on the slope of the second line, which is equal to -2x, and sorry, -2, which is -2 over 1 or 2 over -1. We're going to focus on the -2 over 1 and use that to graph a few points starting off the y-intercept and counting down 2 and to the right 1. Once we have a few points, then we are able now to go ahead and graph and connect these lines, these points. So here we see that we've gotten a rough idea on our graph of where that point of intersection is. But we see that it looks like it's somewhere between 12 and 14 maybe, but we're not sure. We're going to call this the y-intercept with an S on the end. And we want to know where that happens. That's the point where the graphs have the same value, the same height. And we want to know what is the corresponding value of x, where this happens. So in order to solve this, we're going to set the lines equal to each other. So 3x plus 4 equals -2x plus 19. And here you notice that we have a single x in each of these, so all we need to do is solve for x, using all the techniques we always use for solving linear functions for x. So we're going to get x on one side, and we're going to subtract the 4 from both sides so that we have 5x equals 15. And if we divide by 5, we'll get that x is going to equal 3. So this is the x-coordinate of the point of intersection. And now we want to use that to figure out what's the height. Now we can use either function, but it's better to use the one. Usually, unless you just like to do really hard math, it's easier to choose the equation that has the easier math. So here you can see that 3x plus 4 seems a little easier than minus 2x plus 19. So I'm going to just substitute x equals 3 in here and get what the y is. So I get that the y is equal to 13. So I see that my rough sketch was fairly close to accurate. The point of intersection is 3, 13. So let's write that out. Point of intersection is the ordered pair 3, 13. Okay, let's try this again with problem number 4. This is just a little more complicated because here in problem 4, we're given the equations and they're not in y equals mx plus b. We're given first 2x minus 3y equals 6. And then the other one is 3x plus 6y equals 16. And you can see that these are linear equations of lines, because the exponent, the highest value of an exponent on x is 1. Okay, so in order to get to the point of intersection and set these equal to each other, we need to first solve for y. So let's go ahead and start with the first equation and subtract 2x from both sides. And from that we'll get the negative 3y is equal to, and we'll put the 2x term first, so we're in the right form. And then we're going to divide by this negative 3. So we have to be careful with dividing by a negative that we don't lose that negative. And we distribute it appropriately through every term in the numerator. So once we do this, we will get that y is equal to, and now you see a negative in negative 2x divided by negative 3 is positive 2/3 x. And now we're going to have a positive 6 divided by a negative 3. Okay? So we don't want to drop that negative. I see a lot of people who make that mistake. Now we can get the equation of the first line. It's 2/3 x minus 2. All right, now let's move on to the second line and solve it for getting it into y equals mx plus b form. So we're going to subtract the 3x from both sides, and then we're going to divide by 6. And remember, we have to divide each term in the numerator by that 6. So the first one is going to give us negative 1/2, right? Negative 3 over 6. And then we're going to get plus 16 6. There I go. Let me get this cleaner. There we go. 16 6. Okay, and now let's just simplify this 16 6 a little. So we have the minus 1/2 x, and then we can factor out a 2 from the numerator and denominator. Factoring that out, we can 8 factor out a 3. So therefore, now we have our two equations of the two lines that we want to find the point of intersection for. So maybe we can do a little sketch. Like, we don't have to do this. It just gives us some intuition into what's going on. So let's go ahead and try and graph these. The first line is going to be started with a y-intercept at -2, and then a slope of up 2 and to the right 3. So we're going to go up 2 and to the right 3. And that gives us our second point. Now let's go over to 8/3. 8/3 is a little tricky. We're going to put in let's put in one more value for our first equation. So now we see the line for that equation. Now let's go over and graph the second one. And we see that this y-intercept of 8/3 can be written as a mixed fraction of 2 1/3. And so we're going to go up and put the y-intercept just 1/3 above 2. Okay. Now, this is just a rough sketch. We don't have to do anything too precise. And we can use the slope by coming down 1 and to the right 2. So coming down 1 from 2 1/3 is going to put us at 1 1/3. And then we can go over to the right 2. So -1 over 2. And we're just kind of estimate about where we think that this next point is. We know it's at 1 1/3 and for the y value and 2 for the x. So we come over to 2 and we put that point in. And we can do the same thing again. So we take another 1 off of that 1 1/3. We're down near 1/3 and we got to go over 2 to get the right place on the x-axis. All right, so this is just a rough idea of where it is. And now we're going to set these two lines equal to each other to actually mathematically find that point of intersection. So remember now, when we have fractions, we multiply by the least common multiple. And in that case, we have thirds and we have halves. So the least common multiple here would be a 6. So we're going to multiply both sides by 6 so that we can get rid of all our fractions. So on the left side, we're going to distribute that 6 to both terms, and on the right, we have to do the same thing. So on the left, we're going to get the 3 goes into 6 twice, leaving us with 2. So 2 times 2 is 4. So we'll have 4x minus 12 equals, and now on the right we're going to multiply the 6 times -1/2, and we're going to get that to be -3x, and then we're going to see that the 3 goes into 6 twice, and 2 times 8, leaving 2, and 2 times 8 is 16. All right, so now we're going to try and group x by itself on one side and everything else on the other. So we're adding 3x to both sides and adding 12 so that we end up with 7x is going to equal 27. And now we divide by 7 and we get x is equal to 27 sevenths, which is a kind of a weird number, but that's okay. Let's convert it to something that's easy to graph. So 7 goes into 27 3 times, and it leaves 6 sevenths. So that's practically 4. Okay. Now we know where the x value is of the intercept. Now we need to find the y value of the intercept. And we can use either one of our functions to do that, but I think that the one that involves 2/3 x minus 2 looks a little bit easier. So let's go ahead and plug into that one. Okay, so let's go ahead and do 2/3 times 27/7, and then we're going to subtract 2 from that. So we're in a situation where we really have no choice. We're just going to have to go ahead and multiply this out. So we get, first of all, 2 times the 27. We're going to multiply across the numerators. And we see that that's 54, and then 3 times 7 is 21 minus 2. So we're just going to have to get a common denominator. So it's going to be 54 21sts minus, and 2 times 21 is 42. So 42 21sts. And then we're going to go ahead and simplify this and get that this is equal to 12 21sts. Okay, now 3 does factor out of both the numerator and denominator, so we can get 4/7 out of this. And 4/7 is close to halfway between 0 and 1, right? So our point of intersection is 3 6/7 and 4/7. So we see that our graph may have been, our little sketch may have been just a little bit off, but we're pretty close. So we feel confident that this appears to be in the right ballpark. All right, so for the next set of problems, we're going to do something very similar, but we're going to do it with cost and revenue functions. So in problem 5, we're told what a cost function is and what a revenue function is. Let's write that out. So the cost function is 5x plus 10,000 plus 10,000. And then the revenue function is given by 15x. Okay, so we are asked to find the break-even point. Remember, the break-even point is the same thing as the point of intersection. So in order to do this, we're going to set these equal to each other. All right, and now we're going to go ahead and solve for x to find this break-even quantity. So we get that 10,000 is equal to 10x, and now we just need to divide both sides by 10, and we'll see that we get that 1,000 is equal to x. So this is our break-even quantity, and now we need to go find the value associated with this, the y-axis value, or the value from our function. And we can choose either the cost function or the revenue function, but the revenue function's easier to work with. So we're going to go and plug this 1,000 into the revenue function and calculate what that is. So let's go ahead first of all and just identify this and write down that this is the break-even quantity or the value. So let's put in now R of 1,000, and we'll get that that's 15 times 1,000, or 15,000. All right, let's go on to problem 6, which is a similar problem. Just gives us a little bit more practice. So here we're going to set our cost function is equal to 15x plus 12,000. So 15x plus 12,000. And our revenue function is given by 21x. All right, so now to find the break-even point, we need to set these equal to each other. So that would be 21x equals 15x plus 12,000. And subtracting 15x from both sides, gives us 6x is equal to 12,000. And dividing both sides by 6 then gives us that x is going to equal 6,000. So let's go ahead and write that out. 6,000. Okay. So now that we have the break-even point, the break-even quantity, now we want to get the break-even revenue, or some people call it the break-even value. So let's go ahead and choose to plug this value in, the 6,000, into our revenue function. So the revenue for 6,000 is given by 21 times x. So 21 times 6,000. And we can put that in our calculator and get that this is equal to we can put parentheses around these numbers for emphasis, but this is equal to 126,000. So this is our break-even revenue, or some people call it the break-even value. Okay, let's look at number 7. Number 7 is a problem about linear depreciation. We're told an office building is worth $1 million when completed in 2005, and it's being depreciated linearly over 50 years. So let's write down what we know. So it's $1 million in 2005, and it's depreciated linearly for 50 years, which let's just go ahead and write that for now, and it'll help us deconstruct the word problem step by step. So the fact that we know it's depreciating linearly means we're going to need to find a line for the function of depreciation, and we're going to go out to 50 years. Now, we're asked to find the book value of the building in 2010 and then in 2015, but we're told that the scrap value is $0. And this is important because this is telling us the value of this building at 50 years. So it's giving us another point. And we're basically going to be given here 2 points, and we have to find the line that connects these 2 points. So in many ways, this is exactly like the problems you've been doing, where you've been given 2 points, asked to find the slope, and then find the equation connecting those 2 points. So the first point, make sure you see it clearly. It's that it's 1 million is the value at time 0. So whenever we depreciate something linearly, the initial time point is time 0. It's when we get the initial value of this. Oops, sorry about that. So counting this a little more carefully, 1 million is going to, we're going to count by 200 thousands so that we can fit this on our graph. And so we go 200, 400, 600, 800, and then 1 million. And that is the first point in our linear depreciation function. And the second one is going to be the, let's go ahead and write that. T equals 0 for 2005. All right. Remember that our axis here is now time. And we're going to use the fact that the scrap value is 0 at 50 to give us the height of the function at 50 years. So the height, or the value, is 0. So we can go ahead and graph that point. Think of this as the ordered pair 50, 0. And And now we can connect these two lines. This is our function for the linear depreciation of this building. This is a sketch of it. We still need to figure out what it is. This is just to help us get an idea of what it is we're trying to do with this word problem. So let's go ahead and, first of all, get the slope of this line. So the slope we know is given by rise over run. And let's make sure we understand what that is in the context of this problem. It's just going to be the same thing it was before, in the sense that it's y2 minus y1. Remember that that point of the intersection is the coordinate pair 0 and 1 million. And we can associate that with x1 and y1. And we can associate the second point with, we're going to call it t2 and y2, okay, because it's a time. So instead of calling it x1, let's call it t1. The formula is the same. It's still rise over run. And we just have to be careful about the order in which we plug into the formula, that if you put 1 point first in the numerator, you have to use the same points, x or t, associated point in the denominator to be first, right? We have to keep the order right. So here we're saying it's y2 minus y1, and we're going to divide by t2 minus t1. Okay? Make sure that those match up, all right? So t2 is the 50, 0. We're going to put those first. So we're going to put the y2, which is the 0, first, and the t2, which is the 50, first. And then we're going to subtract the y-intercept point, the 0, 1 million. So putting that in, we get it's 0 minus the 1 million value for the building. And then we're going to divide that by 50 minus 0. Now, if you did the math right, the slope for depreciation should always be negative. Okay? Because it's the value at which it's the value that we're going to have reduce in the value of the building per year. So let's write that out. So $1 million for every $1 million is lost for every 50 years. So if we plug that into our calculator, we can simplify that down just a little bit, and we get $20,000 per year is the rate of depreciation. So this rate of depreciation is $20,000. Okay, so now what we need to do is get the function value for the linear depreciation. So for this, we're going to go ahead and use the y equals mx plus b idea. So first of all, it's the function at a time t after 2005. And it's given by the rate of depreciation, which, oops, we need to have a negative, right? 0 minus 1 million is a negative, and a negative 20,000. So our rate has to always be negative. Sorry, I talked about it and then dropped it. Let me make sure that's really clear. This is a negative 20,000. And this is dollars for every year. So we'll go ahead and put that into our linear depreciation equation. Let's go ahead and start writing it out, though, as mt plus b, so we're really clear what we're doing. We're just writing the equation of a line here, and we're just going to put in the slope, and the slope of that line is minus 20,000 times the independent variable here, which is time. So we'll put a t, and then we need to get the y-intercept, which we see right off of our little sketch. It's $1 million. at time t equals 0. So now we have that function, and then we can answer questions about it. So what's the book value of the building in 2010? Well, in order to answer that question, we need to think about what's 2010 in terms of t. Well, it's 2005 plus 5 years. So that means t has to be 5 because we associated t equals 0 with 2005. So in order to get that value at 5 years, we're going to use the function evaluated with t equals 5. Okay, so that's just v of 5 is equal to minus 20,000 times 5 plus 1,000,000. So you see, we start with the million and we're taking away from it more and more every year. That's why it's a linear depreciation. And we can put this in our calculator and find out that we get minus 100,000 plus 1,000,000. And that this is equal to 900,000. So we see in 5 years, the book value of this building went from 1,000,000. So in 2010, the book value is now going to be $900,000. Or was, the book value was in 2010. All right, so what about in 2015? So in 2015, the first thing we have to do is figure out what our t is. So that's 2005 plus 10, right, to get to 2015. So that tells us that t has to be 10. So we can now calculate the value of our building 10 years after we completed it. So it's minus 20,000 times 10 plus 1,000,000. And again, we put this into our calculator to do the math on it. And we get out of this 800,000. So we now see 5 more years and we've lost another 100,000. And every 5 years it's going to be 100,000. And that's because it's the same rate of depreciation across all 50 years. So it's a constant rate and we are just going down until we get to 0. So let's go ahead and write this. In 2010, sorry, I misspoke. In 2015, the building's book value was $800,000. The next problem is also a linear depreciation problem. So let's just start writing what it tells us. It says that in 2007, National Textile installed a new machine in one of its factories at a cost of $250,000. And this new machine is depreciated linearly over 10 years with a scrap value of $10,000. So we're going to go ahead and write this down. So we have 10 for the length of time over which we're going to depreciate the value. And we also know the scrap value, and that is $10,000. So altogether, our goal here with these problems is to find 2 points and then determine the function of the line connecting those 2 points. So remember, if t equals 10, we're meaning 10 years after 2007, which would be 2017. Okay, so let's go ahead and graph this to get an idea of what we're talking about. So first of all, we know that time is on the x-axis, not x, and our time 0 corresponds with 2007, because that's when National Textile purchased the machine for $250,000. So we'll put that as our y-axis.
Okay, and then we're going to
intercept. Put our other information that we have onto our little graph. We know that at 10 years, that the scrap value is going to be $10,000. So we're going to just estimate that here. It may not be that accurate. It's okay. The idea is just to kind of give us a little sense of comfort about what we're doing. So we have these 2 points with a y-intercept at $250,000 and a point at 10,000. So that's our second point. And with that, this problem has now almost been reduced to a regular math problem, which involves finding the equation of a line between 2 points. So let's get the slope of this line. So we know that the slope is rise over run, or y2 minus y1, and now instead of x, we call it t2 minus t1. The important thing is that we keep the order right. So we have 10,000 minus $250,000, and we're going to divide that by T2, which is 10, minus 0, which is the time, when the y-intercept, right, is at T0. So doing the math on this gives us a value of minus 240,000 divided by 10, which is equal to minus $24,000 per year. Okay, so now we have the slope, and we're going to use the slope to come up with the linear equation, the y equals mx plus b form, right? But now it's got a t instead of an x. So let's start writing that. So the value at time t is equal to the slope, which here is going to be, right, so we want it to be mt plus b, right? So we're going to keep that in mind. That's the structure that we're building for our linear depreciation in terms of time instead of x. And we are now going to use the information we found. So we found the slope, which is minus 24,000, and now the variable is t, okay, instead of x, and now we need the y-intercept, which we already know because we were given that at the very beginning at time 0, which is where the y-intercept happens. It was $250,000. Therefore, now we have the equation for the linear depreciation. And then the next thing we're going to do is from this, we're going to evaluate. Oh, no, wait. First of all, it tells us to graph the linear depreciation functions, and we already did that. So we answered B already. Okay, so now we need to go on to answer C. And this is where we're going to evaluate the value of this machine in 2011. So what is 2011? Well, it's 2007, which is time 0, plus 4. So we want to evaluate this function at time t equals 4. So the value of the function at time t equals 4 is minus $24,000 times 4 plus $250,000. So we put this into our calculator and we can do the math. And we see that this is equal to negative $96,000 plus $250,000. And putting this in our calculator, we get that the final answer is $154,000. So what we say is that in the year 2011, this piece of equipment has depreciated and has a book value of $154,000. And then the last question, which is part D, just asks us for what is the rate of that linear depreciation. So let's go ahead and write that. So the rate of the linear depreciation is simply the slope. But because we use the word depreciation, we don't need to put a negative. So we just say the depreciation is $24,000 per year. Okay, so that can be a little confusing. We drop the negative because the word depreciation implies the negative. Okay. The next problem is problem number 9. In this problem, we're asked to find the linear relationship between the dose of something which is given in an adult dose and the, so we're just going to, A is the adult dose. And then we are told that we or that sometimes you convert this for a child using their surface area. And let's just remind ourselves that the dose is given in milligrams. So this is just how I deconstruct a word problem. I start writing down what it tells me, and I start trying to give it variable names. So A is going to be the adult dose, S is the child's surface area, and that's in meters squared. And then I just continue to kind of write down what the problem tells me, trying to translate it into math. So it's telling me now, it actually gives me math. It gives me a function. It says that the dose based on surface area is SA divided by 1.7. And then the first thing that I'm asked to do is show that D is a linear function of S. So really all this is saying is look at what this formula is and look at it in a particular way. So we want to look at this where S is going to be the independent variable. So all we're going to do here is rearrange things. So we're going to rearrange things into a coefficient times S. And that, the idea is that a linear equation would have a slope, and then it would have a slope times our independent variable, and then a y-intercept. So when we look at this, we see that S is what we're going to do a linear function of. Okay, so this is going to be a linear function of S. And now I take this equation and it's not really changing anything. It's just the way I view it. And I'm just reordering it. So I pull out my S and I make everything else a coefficient in front of S. And anything that's not an S, it can be an A, B, C, W, X, Y, Z, it doesn't matter. I will be treating it as a number. So as far as the definition of this function goes, it's only S that's a variable. And notice I can rewrite this function by flipping A and S around and then grouping A with the denominator 1.7 and pulling that out in front of S. So that's how I'm writing this as a function of S, a linear function of S, and I notice that there's no y-intercept. Okay, so then the next question is, if the adult dose of a drug is 500 milligrams, so here we're just going to write down what they tell us, that A equals 500 milligrams. How much should a child whose surface area is 0.4 meters squared receive? So we have a conversion function. This is what our linear conversion function is that we have been given. So we can go ahead and substitute what the A is now. So the idea is you would use this conversion on a bunch of different surface areas for the same dosage. So let's say A is Tylenol, the dosage of Tylenol, and you have a nursery and you have to give everybody a dosage of Tylenol, and the standard adult dosage is 500, and you're going to adjust it based on surface area. So one child in particular, let's say, their surface area is given. And we're just going to do one example where it's 0.4 meters squared. So now we plug this into our conversion formula. And it's going to give us the dose for a surface area of 0.04. So we write in what A is. A is 500 now. And we're going to divide that by 1.7. And then we multiply this whole thing. So we're going to multiply by 0.4. And then we just go ahead and put this in our calculator and obtain the value. And then we see that this is approximately equal to 117.6 milligrams. Okay, so now we finish with that one. And next will be number 10. Okay, and so for this problem, we're going to look for the linear relationship between the Celsius scale and the Fahrenheit scale. And so we start reading it, and we look for information. And what we're told is that the freezing point is 0 degrees Celsius and 32 degrees Fahrenheit. So those 2 points are both considered equivalent. One is in Celsius, 0 degrees Celsius, and the other one is 32 degrees Fahrenheit. So you may, already know this, that water freezes at 32 degrees Fahrenheit, or it can also be referred to as 0 degrees Celsius. So these two are points that help us identify that relationship. So that's one of the points. So then the next thing we're told is that 100 degrees Celsius, when water boils, is also 212 degrees Fahrenheit. Okay, so the first thing we want to do is we want to find an equation giving the relationship between the temperature in Fahrenheit measured on the Fahrenheit scale and the temperature C measured on the Celsius scale. I think it helps to go ahead and just try to graph this out just so we know what we're trying to do here. So consider that the first information they gave us is an ordered pair of 0, 32, and the second one is another ordered pair of 100, 212. And we'll use that to get to think of those as points on a graph so that we can see what is that linear relationship between Fahrenheit, which the way we've identified this, and we could have gone the other way, but the way we identified it is we put Celsius on the x-axis, right? It has the position what normally goes with x, and we have Fahrenheit in the y-axis. And so now we're just going to go ahead and plot the points and the information that we know. So let's start out by putting in the y-intercept, and it looks like it's going to go in at 32. So let's go ahead and count up by 50 so that we can see what we're doing here. So we're going to actually count up by 25s, but we're writing 50 on the every other blue grid mark. Okay, and okay, so now let's just go ahead and give that Celsius axis some values so that we can count and graph out what we're doing. So we're going to go out to 100. And now we'll go ahead and put in our points. So the first point we're going to put in at 0, 32. Okay, and then now we're going to put the second point in at 100 and 212 on the Fahrenheit scale. And that's it. So we are now moved over from a word problem to just a straight math problem. We have a line and we have 2 points. And all we have to do now is use what we already know about finding a linear relationship when you're given 2 points in a line. We first have to find the slope. So this will be rise, which for us, instead of being y2 minus y1, it's f2 minus f1 over run. And this is going to be the, sorry, I'm getting ahead of myself, c2 minus c1. Okay? And so for this, we're going to put in, taking care not to mix them up, but we're going to put in 212 minus 32, and then we'll start with the lower one. Let me get that right. And we'll go with 100 minus C1, which is 0. Okay? So we want to make sure that we keep the points in order. When we're switching variables like this, sometimes it can be confusing, so it's really a good idea to label them well. Okay. So that's equal to 180 divided by 100, which is just 1.8. Okay, and that's degrees Fahrenheit for every degree Celsius. So just to be clear what our units are, they're units of rise over run. All right, so we're going to write that the Fahrenheit, right, because we want a function of Fahrenheit given in terms of Celsius. And this is going to be the slope times x plus mx plus b form, except that we don't want to use x, right? We're going to replace that now with c, which is our input variable, our independent variable, and what we used on the x-axis. So that is the only part of this function that is a variable. Everything else is going to get a number or represent a number. So like before we saw that the little a was even though it was a little a, it still represented a number. So f of c here is equal to 1.8, which is our slope, times the c plus the y-intercept. And the y-intercept, we already know what it is. It's 32. Because we were given that information to begin with. So let's put that in. Okay. All right. So that answers part A. Now, part B says find f as a function of c and use this formula to determine the temperature in Fahrenheit corresponding to a temperature of 20 degrees Celsius. So we've already found the function of f for the Fahrenheit as a function of the Celsius. So we're just going to put in 1.8 times 20 plus 32, and we will get the temperature in Fahrenheit that corresponds with a temperature of 20 degrees Celsius. Okay, so once we put this in our calculator, we get that this is 36 plus 32, and that's equal to 88 degrees Fahrenheit. Okay, so now when we're going to go on to do part C, which is to convert the function that is f equals 1.8c plus 32 to a function of c. So we're going to just want to end up with c equals something. So that's our strategy. We're going to take the current format of this function and convert it. So instead of f equals something, c equals something. Okay, it's really nothing more than that. And we've done some of this earlier on. So let's go ahead and get started. We want to focus on this variable c. So what do we do to get c by itself? We're going to subtract 32 from both sides. And then let's go ahead and write that. So f minus 32 is equal to 1.8c. And then we divide both sides by 1.8, and we're able to get, after we realize that we cancel out the 1.8s, because that's just 1, and we get f minus 32, c as a function of f. Let me be precise. So the Celsius as a function of Fahrenheit is f minus 32 divided by 1.8. And now we're prepared to answer the question about what is the degrees in Celsius when Fahrenheit is 70. Okay, so we go ahead and put this in our linear transformation formula as 70 minus 32 over 1.8, and then we can put this in our calculator, and from that we can get what this turns out to be. So my calculator tells me that this is equal to 21.1 degrees Celsius. Okay, so 70 degrees Fahrenheit is converted to 21.1 degrees Celsius. And all you had to know to make this conversion was that 0 degrees Celsius is 32 degrees Fahrenheit, and 212 Fahrenheit is